In this video, we will learn multinomial probit model to deal with the multidimensional choice problem. Now let's start with a simpler case, a binary probit model. Here we only consider two alternatives, 1 and 2. We also define the utilities for these two alternatives, u1 equal to v1 plus psi 1, and here v1 is the deterministic utility and the psi 1 is the random term. Similarly, u2 equal to v2 plus psi 2. We assume that the two random terms xi1 and xi2 follows a bivariate normal distribution and the mean is 0. We also define the covariance matrix as sigma xi. This equation shows the probability density function of the bivariate normal distribution. With the defined mean and covariance, we can get the probability density function for the random terms. Here, the covariance matrix contains three parameters, sigma 1 square and sigma 2 squares are the variance of psi 1 and 2. Sigma 1, 2 represent the covariance between psi 1 and psi 2. With this definition, we can get the probability of choosing the alternative 1, which is the probability of utility 1 is higher than utility 2. With a slight modification, this probability becomes the probability of psi 2 minus psi 1 smaller than v1 minus v2. Then we can find out the expression of the probability choosing the alternative 1. Here, if sigma 1 and sigma 2 are bivariate normal distribution, then sigma 2 minus sigma 1 is also a normal distribution with the mean 0 and the variance sigma square. Here, the sigma square equals to sigma 1 square plus sigma 2 square minus 2 times sigma 1, 2. In that sense, we can find out the expression of the probability taking the alternative 1. It's a capital phi v1 minus v2 over sigma. Here, capital phi represents the cumulative standard normal distribution function, and the value can be found from the standard normal distribution probability table. Now let's see how we can use the binary probit model to estimate the choice probabilities. Assume that there are two alternatives, 1 and 2, and we have their utility expressions. The deterministic utility for 1 and 2 are also given as 6 and 7. In this example, we assume that the values are given, but in reality, they are usually unknown and they have to be estimated through the attributes. In addition, we assume that the covariance for the two random terms are 0.8, 0.3, 0.3, 0.5. Similarly, we say that the covariance matrix is given in this example, but in reality, they have to be estimated. Then we can record the probability that we estimated from the binary probit model, and then probability of taking utility 1 would be capital phi v1 minus v2 over sigma. Here we need to estimate the value of sigma first. With the defined covariance matrix, we can find out the value of sigma as 0.837. Then the probability of taking the alternative 1 will become capital phi minus 1.19. To find out the value of the probability, we need to go to check the standard normal probability table. In this table, we will find out the value of minus 1.19, and the probability here is 0.117. This is just the probability for us to take in the alternative 1. Similarly, we can apply the same process to find out the probability of taking the alternative 2. Now let's see how we can extend the probit model to multiple choices. At first, we will introduce the Clark's approximation. In this approximation, we define two multivariate distributed random variable, omega1 and omega2. We also know their mean and covariance matrix. And we define omega2 tilde as the maximization of omega1 and omega2, and m2 tilde as the mean of omega2 tilde, m2 double tilde as the second absolute moment, and sigma 2 square tilde as the variance. In that sense, with the Clark's approximation, we find that omega2 tilde is approximately a normal distribution. We can derive the expression of the mean, second absolute moment, and the variance for omega2 tilde. Also, we can find out the values of A and alpha, which will be applied for the three parameters. Let's see how we can apply Clark's approximation for a three alternative case. The probability of taking the alternative k is just a probability that the utility k is the highest one. Then we can make a slightly modification about the probability. It becomes the probability of maximization uj minus uk is always smaller than 0. Here j is not the same to k. With this modification, we can define a new term zj equal to uj prime minus uk, which represents the differences between omega j prime and omega k. Here j prime equal to j if j is less than k, and it's j plus 1 if j is higher than k. That means we will count j and skip over j equal to k. In that sense, we can replace uj minus uk with zj. Then we can apply this modification for the three alternatives case. The probability of taking the alternative 1 becomes the probability that u1 is the highest utility, and we can find out two terms for the z vector. Term 1 is u2 minus u1, second one is u3 minus u1, and then the probability becomes the maximization of z1 and z2 is less than 0. To find out the probability, we have to first estimate the mean z bar and the covariance matrix sigma z for the z vector. Here we will recall the definition of the utility, which would be v plus sigma. And in this example, we assume that both deterministic utility z and the covariance matrix are given. And we also know the expression of z vector as the function of all the three utilities. Then we can write down z vector as the matrix format. It will become u vector times a transformation matrix delta. And this is the definition of delta. With this proposition, we can then estimate the mean and covariance matrix. First, for z bar prime, we have the value as Vm prime times delta, which will give us the value as 0 and 1. Also, we can estimate the covariance matrix sigma z as delta prime times sigma psi times delta. It will give us the 2 by 2 covariance matrix 4, 2, 4, 3. Now we know the mean and covariance matrix of z1 and z2. We can then call Clark's approximation to find out the maximization of z1 and z2. Here we know that the maximization is also a normal distribution with the mean of m2 tilde and the sigma tilde. From the previous estimated z bar and the sigma z, we get m1 is 0, m2 is 1, sigma 1 squared is 4, sigma 2 squared is 3, and sigma 1, 2 is 2. with these values, we can get the value of A and alpha. And then we can estimate M2 tilde and M2 double tilde. And similarly, we can find out the value of phi alpha, which is 0.337. That comes from the definition of the standard normal distribution. And the value of capital phi alpha could be determined through the table of the standard normal probability. For this case, the value is 0.282. With the value of capital phi alpha, we can find out the value of M2 tilde as 1.302 and M2 double tilde as 4.584. Then we are able to estimate the variance sigma 2 square tilde as 2.89 and give us sigma 2 tilde as 1.7. Then we can find out the probability of taking alternative 1. We know that maximization follows a normal distribution with M2 tilde and sigma 2 tilde. Then the probability becomes capital phi 0 minus M2 tilde over sigma 2 tilde. Here we have M2 tilde as 1.3 and sigma 2 tilde as 1.7. It gives us the value as capital phi minus 7659. With that, we can go to check the table of standard normal distribution, and the probability is 0.2216, which is just the probability of taking alternative 1. The Clark's approximation tells how to find out the maximization of two multivariate normal distributed random variables. Actually, this approximation can be extended to more variables. Here, let's see how the approximation can be extended to 3 variables. Assume that omega 1, omega 2, omega 3 are 3 multivariate normal distributed random variables. We know their mean m and covariance matrix sigma. And let omega 2 tilde as the maximizing omega 1 and omega 2. Then we say that omega 2 tilde is also a normal distribution with the mean m2 tilde and variance sigma 2 tilde. And we can find out the expression to calculate the m2 tilde and sigma 2 tilde. Actually, here omega 2 tilde and omega 3 is also approximately bivariate normal distribution with the mean and covariance. Here, for the mean, we have m2 tilde represented by the equation here, which is shown in the previous analysis. Also, we have the value of sigma 2 square tilde. For the covariance sigma 2 3 tilde, it's shown in this equation and represent the covariance between omega 2 tilde and omega 3. Then, as omega 2 tilde and omega 3 is a bivariate normal distribution, we can call Clark's approximation to find out the maximization of these two random variables, which is also the maximization of omega 1, omega 2, and omega 3. And this will give us the way to find out the distribution of the maximization for 3 variables with the Clark's approximation. This method can also be extended to 4 variables. Assume that we have 4 multivariate normal distributed random variables. We know their mean and the covariance matrix. Then from the previous analysis, we are able to find out omega 3 tilde as the maximizing of the first 3 variables. And here, actually, omega 3 tilde and omega 4 is also approximately bivariate normal distribution. And we can find out the mean and variance. These two equations shows the mean for omega 3 tilde and the variance For the covariance of omega 3 tilde and omega 4, as shown in this equation, here we also need to define another parameter alpha 3 to estimate sigma 3 4 tilde. And as omega 3 tilde and omega 4 is a very normal distribution, we can call the class approximation to find out the maximization of these two variables, which is also the maximization of the three random variable omega 1, omega 2, omega 3, and omega 4. The class approximation can be generalized for any number of random variables. Suppose that we have omega 1, omega 2 till omega n as the multivariate normal distributed random variable. We know their mean and covariance matrix. Then we can find out the maximization of these n random variables step by step. First, we will find out the maximization omega 1 and omega 2 as omega 2 tilde. And then we are able to find out omega 3 tilde as the maximization of omega 2 tilde and omega 3. And then we go to omega 4 tilde, and gradually we can find out omega I tilde. Eventually we will get omega n tilde, which will be the maximization of the n random variables. Here we will summarize the generalization of Clark's approximation. Omega I tilde is actually follows a normal distribution with mean mi tilde and variance sigma I tilde. And this equation shows the parameters applied for the distribution. We can get the mean mi tilde, the second absolute moment mi double tilde, the variance sigma I square tilde, and the covariance between omega I tilde and omega I plus 1. We can then utilize the generalized Clark's approximation to estimate the choice probability for multivariate scenarios, which we define as a multinomial probit model. Here would be one general scenario. Assume that there are capital J alternatives and Cn is the set of the alternatives. The probability of taking the alternative K is that the alternative has the highest utility. So UK is higher than the maximum of the utility from the other alternatives. And we can slightly modify the expression a little bit. It will become maximization of UJ minus UK smaller than 0. Here you will find that we are given the deterministic utility for each alternative. Also, we know the covariance matrix for the random term, that is sigma psi. Similarly, we define new variable zj as uj prime minus uk, and it could be written into the vector format. The size of the vector is capital J minus 1, and it has the relationship between z and the utility. Here you need to carefully deal with the index. The index of z is different from the index of the utility u. And with this definition, we can change the probability as the probability of maximization of zj is always smaller than 0 given the mean z bar and the covariance sigma z. Here we can let zj minus 1 tilde as the maximization of z1, z2 till zj minus 1, and then we can call the generalized Clark's approximation to find out the probability of zj minus 1 tilde. It actually follows a normal distribution with mean mj minus 1 tilde and variance sigma j minus 1 tilde. Now probability k becomes the probability of zj minus 1 tilde smaller than 0, and Zj is the normal distribution. From Clark's approximation, we have the equations to estimate mj minus 1 tilde and sigma j minus 1 tilde. And then the probability of taking the alternative k is capital phi minus mj minus 1 tilde over sigma j minus 1 tilde. And that's the way for us to implement the multinomial probit model to estimate the probability of taking any alternatives under the multiple alternative scenario. That will be all about the lecture today. In the next video, we will show how to estimate the probit model.